Another important application of the Lorentz force is the cyclotron. What is a cyclotron? It's a device used to accelerate charged particles to bombard nuclei and trigger nuclear reactions. How does it work? So this is a permanent magnet that has a north pole and south pole here. The north pole of the magnet is on this side, therefore we have on top of this magnet an uniform magnetic field that is perpendicular to the magnet. So it's going to be pointing in the j-hat direction. So if this is the x and y axis. Now on top of this magnet we have this apparatus which basically has a gap in the middle. You can see that when an electron that is in between these two electrodes, it's going to feel an electric field that is provided by this alternating voltage source. So that is attached to these two electrodes. So this electron gets accelerated when it is in the gap, and because this is a charged particle in a uniform magnetic field, it's going to perform circular motion. But it's going to be a circular motion which will have an increasing radius because of this acceleration, while the charged particle is within the gap and feels this electric field due to this alternating voltage source. So why is this alternating? Because the acceleration is in this direction when the particle is going here, and it's going to be in the opposite direction when the particle is on the other side of the gap. So here the particle is accelerating in this direction, here the particle is accelerating in this direction within the gap, because the alternating voltage basically changes the sign of the electric field as the particle performs this circular motion. And eventually it exits from this apparatus with a very large kinetic energy, and we call the radius of the cyclotron capital R. So after being accelerated, the particles exit from the cyclotron. Now when the particle is in the gap, its kinetic energy increases by an amount Q times delta V. So since V increases within the gap, the radius of the circular motion, which is equal to mv divided by qb, because we have mv square over r is equal to qvb. That's within these regions when we don't have an electric field. So this is a metallic structure. Inside the metal we have no electric field, and we have just the circular motion, which is qvb equals mv square over r, so r is mv over qb. So the velocity of the particle increases because it's accelerating in electric field when it is in the gap, and that means the radius increases, so this is going to spiral out as shown in this figure. So when the particle exits the cyclotron, it's going to have a final radius capital R, where capital R is equal to mv final speed of the particle divided by qb. So the final speed of the particle will be equal to the charge of the particle, the magnetic field B, the radius of the cyclotron capital R, divided by m. So it's going to have a final kinetic energy 1/2 mv final square, which is equal to q square b square capital R square divided by 2m. So we have 1/2 mv final square, so we will have m square here, so that will cancel with this m, so this is going to be m in the denominator. So this is the final kinetic energy of the particle as it exits the cyclotron, but we have a word of caution here. If the final kinetic energy is greater than 20 mega electron volts, relativistic effects become important. Now in the discussion of special relativity, we will see that this kinetic energy formula will be modified with the relativistic form, which is gamma minus 1 mv square, where gamma is the relativistic correction factor. So we have to be careful with relativistic corrections when the speed becomes close to the speed of light, or comparable to the speed of light. Okay, so we talked about another application of the Lorentz force, the cyclotron. It's a device that is used to accelerate charged particles by applying them an alternating electric field while they're in the gap, and causing a circular motion due to a permanent uniform magnetic field. And when the particle exits this apparatus, it has a final kinetic energy, which is given by q square b square r square over 2m in the non-relativistic limit. So when the final kinetic energy is greater than 20 mega eV, relativistic corrections become important, and this energetic charged particle is used to bombard nuclei and trigger nuclear reactions.